Alright folks, this class we are going to start section 12.1 in chapter 12. So section 12.1 is congruence axioms for triangles. So firstly, I need to tell you, well, what it means for two triangles to be congruent. So we say two triangles are congruent exactly when there is a correspondence between the vertices such that, and this is the big deal, is that corresponding sides are congruent and corresponding angles are congruent. So remember, congruent means that the measures of these objects are the same. So all corresponding sides have the same length and all corresponding angles have the same measure. If that's the case, we say those two triangles are congruent. We have a little notation for this. So let's talk about that. So if I want to say the triangle ABC, and we use this little symbol to mean congruent, looks like an equals with a little tilde over it. So if that's congruent to triangle DEF, the way this notation works, it tells you the following things. It tells you the corresponding sides, so AB, so that's the first two vertices in this list, that's congruent to DE. AC is congruent to DF, and line segment BC is congruent to line segment EF. So that's what the first bit tells you in terms of sides. And in terms of angles, we know that angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. So when using this notation, you have to make sure you list the vertices in the correct order so that the correspondences make sense. So that's what's going on here. So I want to talk about a couple of properties of congruence that are going to be important for us. And so there's two of them that are very important, but I'll list all three of them. The third one is very handy as well. So the first one says that both for sides and for angles, so any side is of course congruent to itself. This is called the reflexive property. And any angle is congruent to itself. A lot of times we'll take figures that aren't triangles and we'll split them into smaller triangles and then reason about those triangles. So a lot of times these triangles will share sides. So this idea of the reflexive property will be very happy. Everything is congruent to itself. The second one is that Well, we can write it like this. If AB is congruent to CD, then maybe we'll put an if here. If AB is congruent to CD, then CD is congruent to AB. So congruence goes in both directions. This is called the symmetric property. And the same thing with angles. If A is congruent to B, then angle B is congruent to angle A. So congruences go in either order. And the third one, this is called the transitive property. So if your first side is congruent to, say, CD, AB is congruent to CD, and CD is congruent to, say, the next side, EF, then, well, the congruences kind of go together. If AB is congruent to CD and CD is congruent to EF, both AB and EF are congruent to CD, so they're congruent to each other. So AB is congruent to EF. And this is called transitivity, or the transitive property. And with angles as well. So if angle A is congruent to angle B, and angle B is congruent to angle C, then angle A is congruent to angle C. So there are three properties of congruence. All right, here's a quick example of two triangles that are indeed congruent. You can see here that I'm saying that triangle ABC is congruent to triangle DEF. So you can see here length AB, I marked that with 2 ticks. I marked DE with 2 ticks. They are the corresponding sides here in our notation. So the vertex A corresponds with D, B corresponds with E, and C corresponds with F. So the line segments made up of them correspond as well. So DE and AB have the same length. DF, AC have the same length. So here's AC, DF, so you can see they're in the same place in the notation. And BC is the same as EF, BC, EF. And same with angles. Angle A is congruent to angle D. There's angle A with 3 markings, angle D with 3 markings. B is congruent to E. They both have 1 marking. And C is congruent to F. They both have 2 markings. So that's how to use this notation. All right, so we're going to talk about some congruence axioms here. So these are going to be rules that will allow us to determine if two triangles are congruent, if they are basically the same triangle. The measurements about these triangles are the same, they're just in different locations on the page. And that's going to be really important to allow us to prove some results about quadrilaterals or other geometric figures, which is really cool. So a quick note that these aren't provable, at least for us. With a little bit of trigonometry, you might be able to show some of these. But for us, we're going to just take them as rules. And nothing we can prove. These are just rules that are given to us. And kind of the takeaway to all of this, if you know 3 of the corresponding measurements of the 6, remember there is 3 sides and 3 angles, so 6 measurements that you can take of a triangle in terms of length and angles. If you know 3 of the 6 are the same, you know the triangles have to be congruent, except in 2 cases, which we'll get to. There's 2 selections of measurements that don't work. So the first is side, side, side. And the idea with this is take any 3 line segments that you like. There's only one way to fit them together to make a triangle. So if you know that the three sides have the same lengths for corresponding sides, so in this case, let's call this A, B, C, and, well, AB has this one tick mark, so I want to say it's the same as this, so we will call this D, E, F. So since AB has the same length as side DE, side BC has the same length as side EF, and AC has the same length as DF here. Because we know that the triangles are indeed congruent. So triangle ABC is congruent to triangle DEF. So the second one is where you know the following. I'll explain what this means here. So you know two angles, and you know the side that includes both angles, like in this situation. So you have this one side, and you know the angles of the other two sides going across them. So we don't know a priori the lengths of each side, but if you think about it, they have to go in this certain direction because you know the angle. If you know the angle, you know which direction the sides have to go. But if you draw them, there's only one possible place for these lines to intersect, and that gives us our triangle. So if we know one side and two angles, there's only one triangle we get from that as well. So in this case, we know that any triangle where you know that a pair of sides is congruent and the pair of angles that are included in that side is congruent, you know those two triangles are congruent because, hopefully this diagram explains it, there's only one possible triangle you can draw like that. Well, here's the next one. The next one is side angle side. So in this axiom, you know two lengths of the sides. Let's say these are those sides. And you know the angle in between them. So you know the angle where they meet. In this case, you can kind of see by eye how the triangle can be drawn. There's only one possible way, and that way is to just connect the two other endpoints here to each other via a line segment, and that gives us a triangle, and that's the only way to draw a triangle if you know two sides and the included angle, the angle that's made up of those two sides. Here's our next axiom. It's angle side. So in this one, we know the length of one side, we know the angle between that side and another side, and we know the angle between the two sides that we don't have. So we don't have either length of these two sides, but we know the angle between them. So if we think about that, you can see this green line doesn't match up with the end of the line segment here. But to keep this angle the same, all we can do is we can push it in a parallel direction until it lines up with the line segment that we have. So we are going to just move it, move the green line parallel until it matches with the end point of our line segment. So if we do that, well, we keep the same angle here. Remember, we have that transversal of parallel lines property. So this angle here is the same as that angle. Both of these guys are parallel to each other. or at least I try to draw them parallel. And once you get to that line segment endpoint here, you stop. So there's only one triangle that you can get if you know one side, one of the angles made up of that side, and the angle made up of the two sides that you don't have. So that's angle, angle, side. So if you break it down, you can think of it as follows. If you know all three sides, you know the triangle. If you know two angles and a side, you know the triangle. So the other situations we have are two sides and an angle. There's another situation here that we have to look at where we have two sides, but we don't know the angle made up of them. We know, say, one of these side angles. And the other situation is when we know all three angles. They're going to be the two situations where we cannot determine congruence. There's more than one triangle we can make. So the two situations that are non-axioms are when you have all three angles being congruent. We can't say for certain that the triangles are congruent. Because here are two non-congruent triangles. You can see that the lengths of the sides in the left triangle are shorter than the lengths of the sides in the right triangle, even though the angles here are all congruent. So these are two triangles where the angles are congruent, but the triangles are not the same triangle. Obviously, the triangle on the right is much bigger than the triangle on the left, even though the angles of the sides, or the angles between the sides, are the same. The next one is when you have one angle and two sides, but that angle isn't between the side lengths that you know. So what do I mean by that? So let's say one of the sides that we know is this AB. So it has length 1 dot, or 1 slash. Then there's this other side that we know, and it's either going to be BC or BD. I'm going to show you two triangles here, where it has 2 slashes. But we know the angle between side AB and whatever this bottom is. We don't know the length of that because we only know 2 lengths of the sides of the triangle. We don't know this third length. But here are two triangles that are obviously different triangles. ABC and ABD are two different triangles. They're obviously not congruent, even though you have two sides that have the same length, so AB, BC, and AB, BD, and this angle here, A, is congruent in both of them. So you have two triangles that share one angle and two sides, but obviously aren't the same triangle. Triangle ABC is an obtuse triangle. This angle here is obviously bigger than 90 degrees, whereas ABD is an acute triangle. No angle is bigger than 90 degrees. I will say that if you also know the triangle is either acute or obtuse, then you can kind of use angle side side. So you could think of an axiom in some sense as angle side side with the knowledge of being acute or obtuse. There's only one acute triangle that follows one angle and two sides, and one obtuse triangle that follows one angle and two sides. So they are our 4 axioms and our our 2 non-axioms. So these axioms are really important to help us prove some results. And the first result we're going to prove has to do with isosceles triangles. So we have this triangle ABC, and I'm telling you that two sides are congruent, AB and BC. And we want to show if that's the case, we always have the fact that the angles A and C are congruent, that this will always happen. So let's draw a little bit of a sketch just to see what's going on here. So we have that we'll call this A, we'll call this B. I'll call this C. And we're saying that those lengths are the same. And we don't know anything about AC. So we want to show, so I'll put it in red what we want to show. We want to show that angle A has the same measure, so it's congruent to angle C. Now you could think, well, we don't know anything. All we know is the length of two sides. We don't have any angle information to help us out. But what we can do is we can be a little bit clever. We can draw a midpoint of AC, say, call it M. So let's do that. So here's M. And now we know the following. If that's the midpoint of side AC, that means that the length from A to M is the same as the length from M to C. That's the definition of a midpoint. It's in the middle, so it breaks your line in half. So we're going to do that. And then, once we do that, we're going to draw. What are we going to draw? We are going to draw a line segment BM. So a line segment from B to M. So we do that, and we get that our triangle is now split up into two triangles. A left triangle here, say ABM, and a right triangle, CBM. So we have this third side. Let me just put in some line markings for it. We need 3, 1, 2, 3. Now if we look here, what do we have? Well, this left triangle, ABM, the line AB has the same length as the line BC over here in the triangle CBM. I know AM has the same length as CM, and I know BM, well, that's the shared side, so obviously it has the same length as itself. We have that reflexive property. Every side is congruent to itself. So, this left triangle and this right triangle, we found that it has 3 corresponding sides of the same length. And remember, we said there's only one triangle where that's the case. It might be flipped and moved around the page, but we know that those triangles, ABM and CBM, are congruent. And if they're congruent, it means that all the angle measures also have to be congruent. So let's write that up. And one good way of writing it up is using something called a two-line proof. Let's do it. And kind of the easiest way of doing it is just draw a line down your page. On the left-hand side, we're going to have the result. And on the right-hand side, we're going to have the reason we're allowed to say that. And I like to number these as well, just so I can refer to them. Let me explain what I mean. So, let's write down what we know. So, we know the first one, we're given that line segments AB and BC are congruent. And how do we do that? We know that because we're given that in the question. So we can just write the word given, and that's what that means. The second thing we know, well, M was a midpoint. So we know that AM is congruent to CM. We know that for sure because M is a midpoint. And that's how we know it, so that's what I'm going to write here. Since M is the midpoint, of line segment AC. It splits it in half, which means that each half has the same length. And the third thing we know, because what I want to do is I want to use side, side, side as my axiom to prove that these triangles are congruent. So I need that third side, and it's a shared side. BM is shared among the left triangle ABM and the right triangle CBM. So I'm going to write that down. I'm going to write that BM is congruent to itself, to BM. And how do I know that? I know that by the reflexive property, because everything's congruent to itself. So, what do I have here? I can reason from that that, well, AB is congruent to CB, AM is congruent to CM, and BM is congruent to BM. So I have this correspondence of vertices. So A corresponds to C, B corresponds to B, and M corresponds to M. So I can say that triangle ABM is congruent to triangle CBM. And maybe you wanted to write those in a different order. Maybe you wanted to say it was triangle BMA and triangle BMC. It's as good as the other. It doesn't matter as long as the correspondence of vertices match. So A corresponds to C, B corresponds to B, and M corresponds to M. So as long as you have that correspondence correct, you're using the notation correct. Now, I know that's the case because I used the side. Oh, give me 1 second. The side, side, side axiom. And why was I allowed to use that? I like to tell people how I knew that. Well, how did I know that the corresponding sides were congruent? Well, I knew that the first pair of corresponding sides, AB and BC, because of line 1. So I'll tell people that was because of line 1. The second pair of sides, AM and CM, I knew that from line 2, so I'll tell people line 2. And the third side, of course, it's just another copy of itself. They share a side, and I knew that from line 3. So I like to tell people why I'm allowed to use the side, side, side axiom. All right, so now I have that these two triangles, ABM and CBM, are congruent. There they are there again. And remember, once I know two triangles are congruent, I know every measure about them is congruent. Particularly, I know these corresponding angles, angle A and angle C, are congruent. So I'll write that down. I know that angle A is congruent to angle C, and that's what I wanted to show. And how do I know that? I know that from line 4, let's say by congruent triangles. And I know those triangles are congruent from line 4. And I will say, in the book, you'll see them write, instead of congruent triangles, they will write C, P, C, T, C, which means corresponding parts of congruent triangles are congruent. So you can write that if you want, but that kind of hides the meaning a little bit. I just like writing congruent triangles. You know that corresponding parts of congruent triangles are congruent. So we know angle A is congruent to angle C. That's all we need to write, because that's what we needed to show. But what we also get for free is we also get angle ABM, that's this guy here, is congruent to angle CBM. That's that guy there. So we get that those are congruent for free. And we also get that angle AMB is congruent to angle CMB. So these angles are congruent. In fact, we know they're congruent and they're supplementary since they break up a straight line, we know that they both have to be 90 degrees since they have to have the same measure because they are congruent. All right, let's do one more example, and then that'll be it for this class, and we'll move on with some more examples for the next class. So here's our problem here, and it's the opposite thing. So we want to show the other way. So if we know that two angles are congruent in a triangle, then we know that the sides are congruent. So let's start out by drawing a diagram. It's going to be the same idea. We assume the if part is true. We show that the then part is true. So let's draw our triangle. So here's our triangle. So this is A, this is B, this is C, and I know that angle, what was it, angle A is congruent to angle C. So this is what I know. And I want to show that AB is congruent to BC, those sides. So I want to show that those sides are congruent. Remember, I don't have that. That's what I want to show. So I'm going to do something incorrect here. But that's okay. Sometimes when you're proving results, you can kind of see that it's okay to do things that are incorrect and then start again. So one thing we could do is we could just do the same thing. We could pick the midpoint M, and I will do that. And I will draw a line. I know these guys are the same. And I know that that shared side is the same. But if you look at this, we don't know too much about these triangles. We don't know anything about any of the other angles. So what we have here is we have that angle side congruent. So we know the lengths of two sides are congruent in these triangles, and one of the non-included angles. So not the angle that's between them. So that's the angle side. So that's not a congruence axiom. So this gives us angle side. Maybe I'll write that, which is bad. So we can't use that to show that the two triangles ABM and CBM are congruent. So we have to come up with another way. So this is no good, but that's okay. Let's draw it again. It'll look a little different, but the idea will be the same. So again, this is A, B, C. And we know that those angles there are congruent. What we can do instead is we can pick a point on our line here, X, that cuts the angle. If we make a line segment BX, we can pick that point X so that these two angles here are congruent, ABX and CBX. So let's do that. Let's pick point X on line segment AC such that angle ABX, and I'm using this 3 vertex notation for angles here because I can't just say angle B, so that is congruent to angle CBX. And if I do that, now, well, this third shared side obviously is going to be the same length. Now I have two angles and one side of each of these triangles be congruent. So on the left side, I have angle A being congruent to angle C, and angle ABX being congruent to angle CBX. And by reflexivity, because it's that shared side, I know that BX is congruent to BX in both triangles, of course. So I can use that angle side. Whenever you have two angles and another side, it doesn't matter where that other side is, you know that those triangles are congruent. So now we can use one of our axioms. So now that we know what's going on, once we have that these triangles are congruent, we know all the parts of them are congruent. In particular, the one we care about is that AB is congruent to CB. Once we have that, we're good to go. So let's write this up. So it's the same idea. Let's do a two-line proof. We'll have our results here and our reason here. So the first one is, of course, that angle A is congruent to angle C, and we know that because that's given to us in the question. The second thing we know is that angle ABX is congruent to angle CBX. And we know that because we pick the point X such that line segment BX bisects. Bisects just means splits an angle directly in half. So it bisects angle B. And maybe I'll just define bisects for you here. So bisects means splits an angle in half. So that's how we drew that line segment there. We picked it so that it bisected angle B. So that's 2. And the third one, of course, so we have our two angles. We also know that line segment BX is, of course, congruent to line segment BX. And we know that by reflexivity. So reflexive. Okay. So we can reason, because we have those two angles, angle A and angle C are congruent. The other two angles, angle ABX and angle CBX, are congruent. So that's angle. And we have the shared side. BX is, of course, congruent to itself. We can use angle side to say that those triangles are congruent. So let's do it. So triangle ABX is congruent to triangle CBX. And I'm being careful to make sure that I list the vertices in the order of their correspondence. And how do we know this? This is by the angle side axiom. The first pair of angles I know by 1, the second pair of angles I know by 2, and the side I know by 3. So I always like to tell people how I know all of this. And then finally, well, we know that the left and the right triangles are congruent. So we know everything about their measures is congruent. In particular, we know that AB is congruent to BC. So let's write that. So we know line segment AB is congruent to line segment BC because of the idea of congruent triangles. And we know that by 4. We know ABX is congruent to CBX, so we know everything about the measures is the same. And that's how to use these axioms to be able to prove results about shapes that we know. And so what do we got? Kind of putting these two together. Let's write that as our final thing. So putting these last two examples together, what do we have? We have that a triangle has two congruent sides exactly when it has two congruent angles. So the first example we said, well, when it has two congruent sides, does it have two congruent angles? And we found yes, it does. And then we have to say, well, is there any cases where we have two congruent angles but not two congruent sides? And it turns out it doesn't. When we have two congruent angles, we always have two congruent sides. So these are, of course, called isosceles triangles. So isosceles triangles have both two congruent angles and two congruent sides, and there's never a situation where we have one but not the other.